Okay, so this is the first question that we're going to do today. So we're going to do a few free responses and a couple multiple choice. This is the first question that we're going to do. All right, so you're going to do it on the boards, and then we'll come back, and I'm going to pause the video while you're doing it, and then we're going to come back and talk about it. Okay, so the answer is B. You're going to use the first, right? The first order equation. You're going to plug in, you have the half-life, which is T1 half, which should get you K, right? You have, what do you have? You have the starting? No. You need 1 milligram, so you have the end, and the half-life is 12 hours, right? Okay. No, the half-life is 2 hours, and it's going to take 12 hours, so you have time t, and you have the mass at time t, so you need to know the original amount that is shift. So you plug that in and you solve, okay? All right, so here comes the next problem. The next problem is a free response problem. I'm just looking for it. Oh, here it is. I have that problem. Nice. Okay. All right, here is the free response problem. That's weird. Where'd it go? Oh. What's going on? What is happening? All right. Okay. Here's the equation. 2C4H6 gas yields C8H12 gas. Hang on. It's a little complicated here. Hang on. There we go. All right, hold on. Okay. All right, so there's the equation, right? All right, at high temperatures, the compound 1,3-butadiene, look, buta, four carbons, right? Butadiene. Okay, so it has two double bonds, see that? All right, reacts according to the equation above. Here's the equation. The rate of the reaction was studied at 625 Kelvin. I'm going to have to move it up because there's 3 graphs, so write that down, 625 Kelvin. In a rigid reaction vessel. 2 different trials, each with a different starting concentration, were carried out. The data were plotted in 3 different ways as shown below. Here they are. Here are the 3 different ways. Okay, hang on. Okay, wait. Okay, there you go. There are the 3 different ways. So let me highlight because it's hard to see. The concentration of the 1,3-butadiene, you can already see where this is going, right? The logarithm of the concentration of the C4H6, and the 1 over the concentration. Here are the questions. A, for trial 1, right here, calculate the initial pressure in ATM in the vessel at 625 Kelvin. Assume that initially all the gas present in the vessel is C4H6. So what do you have? Moles per liter. Oh, I hope some of you are getting this, right? Okay, good. So let's see. In trial 1, which is the circles, in trial 1, calculate the initial pressure. So I'm going to zoom in on this, right? In trial 1, because this is, I don't know what to zoom in on to help you. This one, is that the one we want? Okay, that's the one, we're agreed that this is the one we want here? Okay, so I'm gonna zoom in on this one. Zooming in. 625 Kelvin, what is the initial pressure? Assume that initially all the gas present in the vessel is C4H6. What is the initial pressure? .0821 Latham riding a camel, right? Or .08206. I think that's what we use, right? Oh, Grant, you need to look at your calculation. Okay, ready for number 2? Number 2, use use the data and use the data plotted in the graphs to determine the order of the reaction. Use the data plotted in the graphs to determine the order of the reaction. Ms. Paxton warned us we were going to have to do this, and we didn't believe her because we didn't see any in graphs. And then she brought out the 2016 test, which was only 6 years old. And we said, no, Ms. Paxton, we're never going to have to do that. And then she brought us out the end of the year test, and she said, this is the plastics exam from 2020. And there it was again. I'm just saying. Use the data in the graph to determine what order is it. Okay? Letter C, the initial rate of the reaction in trial 1, the initial rate, so you might want to write this down. The initial rate in the reaction in trial 1 is 0.0010 moles per liter second. Calculate the rate constant, comma, K, comma, for the reaction at 625 Kelvin. Do you want me to repeat? Okay. The initial rate of the reaction in trial 1 is 0.0010 moles per liter second. Calculate the rate constant K for the reaction at 625 Kelvin. It shouldn't matter, right?
Oh, yeah, you're right.
Okay, now when we finish, I have 4 examples of people's work, which has been graded by graders, and it says like, this is a 3 answer, this is a 1 answer, this is a 5 answer, this is a 4 answer. so you can see what your answer will actually be. Okay? Take a trial, any trial. Okay, are we ready? The graph? B? Like which one was linear? No, graph C is linear. This is linear. B? Question B? Uh-huh. Yeah. Yes, because when it comes to rates, you don't care about the products. The only thing you care about are the reactants. Yeah, yeah, because your rate equation has the two, but then you have to solve for the. All right, ready? Here we go. Question number 1. The answer is 1.0 ATM, and it is worth 1 point for the correct setup, which should look like this. 0.2 moles, 0.08206 liters ATM moles per Kelvin, right? And then 625 over 1 liter. And your answer should be 1.0 or, in fact, 1.03 ATM. And that is a 2-point question. So give yourself 2 points for that if you got that right. If you only got 1 and you got the answer wrong, then you only get 1 point, okay? Question B, second order. The reason is because this is the linear graph. This is definitely not linear. I mean, if you had questions about this one, fine, but you definitely don't have questions about this, and there's 2 trials here, okay? And this one is definitely not linear. In fact, this is the decay graph, okay, the concentration. So you can tell, remember, second order, this is the decay graph. So this is definitely the linear one where both of them are exhibiting linear on 1 over. So that makes this a second order equation, okay? Which, if it's a second order equation, your rate is going to be equal to K times the concentration to the second order. That is the equation. Second order. And it's second order because your linear graph is 1 over the concentration, all right? Okay, letter C. So this is going to be the hardest question, right? But if you didn't get this, you're not going to be able to get this one, right? Okay, letter C. So we're going to take the rate equation. We take any 2 points, but they have to be concentration points, right? So we take 0.2. That's the concentration, right? At the rate. So we're going to take 0.2 and plug it in. All right, 0.2 over the initial rate. Here's the initial rate, 0.2. See that? Right? And then we're going to plug that in. the initial concentration over the rate. Now you can plug it in here if you want, that's fine. Plug it in here to your initial rate. So looking at the graph, here's my initial concentration. What is my rate at that initial concentration? So here's my initial concentration, and they tell me what my rate is. Then I'm going to divide that out, and I'm going to square it. And that's going to give me my K of 2.5. That's it. That's all you have to do. Where did I get my initial concentration? From the graph right there. And they gave me my initial rate. This formula? This? This? Here? So I took rate equals K times the concentration of A squared. We're all agreed on that. Okay, then I plugged in what they gave me, 0.0100, which was my rate, is equal to K times, I looked up my initial concentration, right? 0.020 squared, and then I solved for K, okay? Right?
Why is time not included?
Oh, because, well, so why is time not included in that equation?
Oh, wait, this is a different equation. It's rate equals.
Oh, because, wait, I got the answer to this. So, all right, why is time not included in this equation? This, we're using the differential form. Differential is concentration versus rate. Yes, that's correct. Rate is rate and versus concentration. That's correct. So if you looked at it, mx plus b kind of thing, right? Okay. All right. Next